Hello, and welcome to Module 12, Lesson 1, which is an overview of oceans. All right, so the focus question today is how did Earth gain its oceans? So, just a review on vocabulary: lake is a natural or man made body of water, and that's formed from maybe glaciers, maybe dams like Whiskeytown and Shasta, or just natural little areas like in the Trinity Alps where we've got mountains. All right, so we're starting oceans, and oceanography is a scientific study of Earth's oceans. And we use a variety of technologies. So we use satellite images, we use sonar, we use floats, submersibles, computers, all kinds of things to analyze and study a huge variety of things in the ocean. So we study geology of the ocean, we study volcanism in the ocean, we study salinity, we study sea creatures, ocean currents, weather, all kinds of things. So the ocean really is kind of the backbone of Earth. All right, so if we look at studying things on the surface of the ocean, we use sonar. So if we're floating on a boat and we're wanting to study the depths of the ocean, we could use something called sonar. So that's sound, navigation, and range. And so there's a variety of different kinds. We talked about this at the very beginning of the year, but dolphins use sonar. Bats use a type of sonar called echolocation. Um, Whales use sonar, so they basically are just sending out waves of sound, and when it hits something, it bounces back, and that recording, whether on a computer or in your brain, like an animal, they would detect that, and they could tell how far away things are based on where it hits. And so there's different types of sonar. There's side scan sonar, which is basically sending the signal out the side of a boat, and it's mapping the topographical features. So we're mapping the different elevations and things like that. We use something called JSON, OSTM JSON. We learned about that at the beginning of the year. And so that is giving us measurements of height. So how high is the ocean? And it can measure differences in centimeters. So for example, during El Nino, when we have a pooling up of the warm water up against South America, we can detect that using OSTM JSON 3 satellite. And we can figure out if it's gone up 2 centimeters. So it's pretty amazing. But also looks at temperature, currents, and wave conditions as well, not just sea surface height. All right, so in the deep sea, we use submersibles. So we send submersibles down into the water, and we can look at things. We can study, analyze the ocean bottom, do all kinds of things. And then, of course, we use computers to analyze and figure the hard stuff out for us. All right. So in the oceans, if we think about where all this water came from, scientists think or hypothesize. And remember, hypothesis in science is an if-then statement. So if something occurs, then this will happen. So there's a variety of reasons. So comets and meteorites actually contain quite a bit of water. So those are two remote sources. And so early on in Earth's formation, we had lots of comets and meteorites bombarding the Earth constantly. So that can accumulate water slowly but surely. And then also there's water vapor in rock and contained within the earth as well. So if we look at this last bullet, it says if early Earth contained the same percentage of water as meteorites, 0.5%, it would have been sufficient to form early oceans. So they've done a lot of tests on this, and comets and meteorites alone are enough to contribute to the amount of water that we have on Earth today, which is pretty amazing. And then volcanism. So I mentioned that deep in the Earth we have water vapor trapped. And so as volcanism occurs, which is just a volcano erupting, we get large quantities of water vapor that go into the atmosphere. And so those can also condense and form water and can condense and form the oceans as well. All right, so if we look at this, and early on Earth, when it was forming, lots of volcanism. So volcanoes constantly, all the time. And so we've got volcanism here, volcano erupting. It releases nitrogen, chlorine, carbon dioxide, hydrogen, water vapor. And then it condenses into clouds and precipitates and eventually accumulates enough to form our oceans.
3/4 of Earth is covered in water. It's why it's called the Blue Planet. But imagine Earth without its oceans. And instead, with all the water in the world gathered together in a ball. There's not that much, really. But this water is what makes Earth different from every other planet in the solar system. The oceans have been here for almost 4 billion years, carving the coastline, driving the climate, and controlling the destiny of life itself. But 4.5 billion years ago, when our planet was born, it was just a molten inferno. There was no place for any liquid water at all. Yet the ingredients needed to create water were there, locked away deep inside the Earth when the planet formed. As the first volcanoes erupted, one of the gases that billowed out was steam, and as the planet cooled, it formed clouds. It rained for thousands of years. As the first rivers formed, they began to fill up the lower-lying areas on our young planet, possibly creating the first oceans. But it's reckoned that even this relentless downpour only delivered around half the water that makes up our oceans today. The rest came from outer space. This is a comet, filmed in 2005. It's about 4 miles across, and like all comets, it's made of rock and water in the form of ice. To discover just how much water comets contain, scientists deliberately crashed a space probe straight into it. After it ploughed into the surface, more than 250,000 tons of water burst into space. In Earth's formative years, it was hit by thousands of comets like this. By the time the bombardment finished, it's thought they'd delivered up to half the water in our oceans.
All right. Oops. I want to watch it again. All right. So the oceans contain about 97% of the water found on Earth. The other 3% is fresh water, and that's located in the ice caps. Rivers, lakes, underground sources, and locked in glaciers in Greenland and Antarctica. So Earth is known as a blue planet because of that, because there is 71% of the Earth's surface is covered in water, in oceans. So pretty amazing. So if we look at the distribution of water, the Northern Hemisphere, we've got 61% oceans. So this is looking down from the North Pole. And then the Southern Hemisphere is 81% ocean. So really we have a lot of land mass in the Northern Hemisphere, like we learned with climates. We don't have temperate climates in the Southern Hemisphere because this is where the temperate climates would be, and that is just the Southern Ocean. So definitely a lot more ocean in the Southern Hemisphere. All right, so if we look at sea level is the level that the oceans are at. Excuse me. And that changes. So it changes with the tides, but it also changes with glaciers. So if glaciers are melting. And so then we have higher sea level. So glaciers melt and the sea level goes up. And when glaciers form, like during ice ages, then the sea level goes down. And so we can see during warming periods, we have higher sea level. During colder periods, we have less. All right, and so we look at these sea level changes, and so notice from 1994 to 2015, the level has gone up. This is in millimeters, so remember we're measuring this with the JASON satellite. So it's gone up 60 millimeters, which is 6 centimeters. So that's quite a bit. It's average about 3 millimeters a year, and this is because the glaciers are melting. And so with glacial melting, we get ocean sea levels rising. All right, here's our major oceans. So there are 3 major ocean basins. They're all connected together. So you can see, even though they're separated in names, they're still really, the water mixes. So we've got the Indian Ocean, Pacific Ocean, Southern Ocean, Arctic Ocean, and Atlantic Ocean. So those are our 3, those are our main oceans, but the 3 major oceans are Pacific, Atlantic, and Indian. The Southern and the Arctic are small, but these 3 in the middle are major oceans. Oceans are a big source of oxygen, and so they're about 50% of the oxygen on Earth comes from the oceans. They also hold carbon dioxide, like we learned a couple weeks ago. So they hold a lot of CO2, and if they increase their CO2, if we have more CO2 in the atmosphere, then it causes more CO2 in the oceans, which causes acidification, and so it also regulates temperature. So the oceans regulate heat from the equator up to the poles. All right, and then if we look at the composition of seawater, this is looking at the North Atlantic and North Pacific. So looking at oxygen levels, notice how oxygen levels are fairly high at the surface. So here's the depth as you go down. So they're about the same in the North and Atlantic and Pacific. But then notice what they do in the Pacific. It takes a dive. So this is upwelling. So we talked about upwelling. That's along the coast, like of California. And we have water coming up from the bottom, and that's bringing lots of oxygen, nutrients. So that's why it's high at the surface, but then drops dramatically. And so the North Pacific, as we go down in depth, it decreases dramatically in oxygen levels. And then the North Atlantic stays pretty steady. And then silica, we've got the North Atlantic versus the North Pacific. We've got quite a bit of silica, and this is basically from runoff. So in the North Pacific, we have more runoff from landmass than we do in the North Atlantic. All right, and then salinity varies too. So salinity is the amount of dissolved salt in seawater. So salinity varies. If it's very hot, then it's going to be very salty because we've got evaporation occurring. And evaporation occurs, salt's left behind. So water is the only thing that goes up into the atmosphere. And we measure this in parts per thousand. And we'll do a lab towards the end of this week that will look at salinity levels. So we'll do that at the end of the week. But salinity is just the measure of amount of salt in the water. And so average is about 35 parts per thousand, but it varies. So like I said, in the Red Sea, up here in the very arid areas, it's very, very salty. And then over here, where we've got lots of precipitation or runoff, like the Mississippi River, fresh water going into there, we have not very low, but we have lower salinity. And that just depends on how much fresh water is in the ocean. All right, so a mixing of fresh and salt water is called an estuary, and estuaries are actually really important. The Bay Area is a big estuary, so we've got the Sacramento River flowing into the bay, and that is a mixing of fresh and salt water. And so it's a really big kind of nursery for organisms. So it's really important for organisms. A lot of nurseries are there where babies are born for both marine organisms and land organisms. And also, if we think about like the salmon coming up here and spawning, estuaries are really important because salmon go from saltwater to freshwater, and they can't do that overnight. So they have to regulate their bodies, and they're one of the only fish that can do that. can go from salt to freshwater and back. And so they have to acclimate their bodies. So they have to sit in the estuary for a while till their bodies get used to freshwater before they can migrate up here to spawn. And so without the estuary, they would not be able to do that. So estuaries are very, very important. And the salinity is, you can think of it as 50%. So it's kind of a mixing of fresh and salt water. All right, and then if we look at the source of sea salt, so where does this sea salt come from? So basically, it's found in rock. And so when rock dissolves, the salts dissolve into the water. So think of like limestone dissolving or other rocks breaking down or weathering. And so that releases those salts, and it's pretty steady over time. So we can look at salinity levels millions of years ago locked in the shell and fossil record, and we can see that salinity levels are about the same as they were millions of years ago. And then we also have some chlorine ions and salts forming from volcanic eruptions as well. All right, and then removal of salt. Salt comes out of the ocean and stays at a steady rate because it's being put into the ocean, but it also comes out. So basically, marine organisms, when they're forming their shells, they absorb salts and they use that to build bones, teeth, shells. And then, of course, it goes back in because of the volcanic eruptions and dissolving. So it stays pretty steady. Even millions of years ago, it stays pretty steady. All right. And then some more thinking about things that are going on in the ocean. The pH of the ocean can change. So if we have more CO2 being absorbed, then the pH can go up. So the average is about 8.1. 7 is neutral, but 8.1 is a little bit basic. And so when there's more CO2 in the ocean, it absorbs, it makes it more acidic. And it's gone up. Move this little thing out of the way. It's gone up from it's gone from a pH of 8.2 to a pH of 8.1, which doesn't seem like that much, but it's powers of 10. So this is actually about a 30% increase in acidity. And so that's since the Industrial Revolution. And the Industrial Revolution is when we started burning lots of fossil fuels. And we talked last week about fossil fuels, and those put a lot of CO2 in the atmosphere, and that's absorbed by the oceans. So that's causing acidification, which is causing corals to bleach and organisms to not be able to produce sufficient shells. All right, and then density. Density changes in the ocean water. We've got cold water is more dense. Warm water is less dense. If we think about salinity, if we increase salt, it's going to make it more dense. And if we increase temperature, it's going to make it less dense. So warming oceans become less dense, so they expand and they actually get bigger as far as sea level. So, and then also the density changes as well. So you've got warm water is less dense, salt water is more dense. So this constant fluctuation is causing density differences and changes in the ocean. But just understand density. So we will talk a little bit about that in that lab I'm talking about for oceans. But cold water is more dense, and just like cold air is more dense. And then saltier water is heavier, so it's more dense as well. And then the freezing point of water. Freezing point is actually lower than regular water, and that's because it's got salt in it. So salt lowers that freezing temperature to -2. Normally fresh water is 0, but salt water is -2, so it freezes at a much colder temperature. And then if we look at light, light is absorbed different. If you guys have ever been scuba diving or snorkeling or, swimming around with goggles on in the lake, you've probably noticed that colors are different. So if we go into the ocean, if we look at depth, so about a range of 100 meters, you can see red disappears real fast. So about 20 meters, red starts to disappear. And then basically below a depth of 100 meters, all we see is blue light. And so this photosynthesis, because photosynthesis needs all the colors, occurs in this top portion. So the top portion of light, or top portion of the ocean, is extremely important for photosynthesis and that 50% of the oxygen that's being released into the atmosphere. So in general, this last bullet, light penetrates only about the upper 100 meters of ocean. And below that, it's just blue light, filtered, very small amount of light that penetrates through. So So that's why it gets dark in the ocean very quickly. And this is very small compared to the whole ocean. The ocean is, 7 miles deep in some places, and 100 meters is not even close to that. So most of the ocean is very dark. All right, and then if we look at this layering of oceans, we have something called a thermocline. And so this is tropical water, very warm. And then here's depth. And so you can see it's warm for a while and then it drops. And then you've got temperate regions, which is like where we are. So you can see it's a little bit colder, not a much difference. But notice when you get to a certain point, about 1,000 meters, it doesn't matter if it's coming from the poles, if it's coming from the middle of the earth or the tropical region, it's all about the same temperature. So about 1,000 meters, we've got about the same temperature throughout the entire world of oceans. But this temperature difference right here is called a thermocline, which is right here. So it's just a transition of ocean layer that lies between warm sunlit water and the bottom. Well, not the bottom, but 1,000 meters down. And so you've still got miles and miles of ocean that are relatively the same temperature. All right, and then this last little bit, deep water masses. So what happens is cold water is more dense. So when we've got this ice caps breaking off or sea ice melting, it says surface water is cooled by cold air temperatures. As ice forms, salt is left behind, so it becomes more salty, so it's more dense, and it's more cold, so it's more dense. So our densest water is found at the poles, and that's really important. So our densest water is found at the poles. It sinks and carries all the way down to the equator. And at the equator, we've got warming occurring. So we've got this huge circulation of water that's occurring on Earth. And so that's what this is showing. So this is our coldest, densest water. And so that's sinking to the bottom. And then you've got things going on at different depths. This is the North Atlantic deep water. This is the Antarctic intermediate water. We've got the Antarctic bottom water. You don't need to memorize these or anything, but just understand that there's lots of deep water circulation of oceans. And we'll look at that at that lab I was talking about at the end of the week also. And that's it. I hope you enjoyed.